Hi, and welcome to this last lecture in clinical engineering. This week we are going to look at neurological measurements. Okay, we are continuing in our subsection on the module on medical devices. The basic idea in this module is to give you an idea of the various kinds of technology that is used by clinicians in their practice, right? And of course, we can't give you an exhaustive overview. What we are trying to do is select certain subsections, and because I'm teaching, I'm selecting subsections that I'm familiar with, and I'm just kind of going through the medical applications of technology, right? So this week we're going to look at neurological measurements. So first of all, what do I mean by neurological measurements? Now, you have already studied the nervous system as a part of your anatomy and physiology module, and you know that the nervous system can be broken down into two parts, right? The central nervous system, which basically consists of the brain and the spinal cord. And you also have the peripheral nervous system, which consists of, you could say, the spinal cord, the nerves, and the muscles, right? So uh, neurological measurements are measurements that look at the integrity of the nervous system, right from the brain, through the spinal cord, through the nerves, into the muscles, right? So you want to check whether there is some problem in the nervous system. How would you do that? What you do is called neurological measurements. Sometimes you also call it electrodiagnostic tests, but electrodiagnosis is basically used uh, for the peripheral nervous system alone. But what we want to do is we want to study tests for the peripheral nervous system, which we'll do. But we also want to look at the central nervous system, tests like EEG and evoked potentials. And we'll look at those as well in the coming lectures. All right. So, but this is our first video, and in this video we want to explore or give an overview of the anatomy and the physiology of the nervous system. Okay, we are not going into too much detail. I know that you hopefully know all this, but let me just point out a few things that I think are relevant to the discussion in this lecture. So, how is the sensory system of our body organized? Now, the nervous system can also be divided into two parts. So we divided earlier into the central and the peripheral nervous system, but you could also divide the nervous system in terms of the sensory system and the motor system, right? The sensory system is the part of the nervous system that gets sensations from various places in our body to our brain. The motor system is the execution of movement by our muscles because of signals sent by the brain, right? So motor system works from the brain to the muscles, while the sensory systems works from the periphery, the various sense organs, to the brain, right? So we are looking at the sensory system in this particular slide. How does it work? Now, let's say you have a sensor at the tip of your finger, and you could have different sensors, right? You could have mechanoreceptors, pressure receptors, pain receptors, temperature receptors, so whatever they are, okay? So if there is a sensor here, the sensor, how does the brain know what the sensor is sensing? It knows it because there is a nerve connecting that sensor to the brain. Not directly, but there is a nerve going to the spinal cord, and through the spinal cord you have a signal sent to the brain. Now in the brain, the all the sensory nerves end at what is called the somatosensory cortex, and in this cortex, in this place, the sensations are organized spatially. So if there are different parts of the brain for example, for sensations from your hand. There is a different part of the brain for sensations from your face, and so on and so forth. Okay, and depending on how much amount of brain is devoted to the sensory parts, to a particular part of our body, we have more sensation or less sensation at different points in our body. Okay, hopefully that's right. So let's carry on. How does motor control work? Now, motor control works the opposite way, right? You start from the motor cortex, probably even before that from the basal ganglia, and you have signals from the basal ganglia going to the motor cortex. Motor cortex plans and initiates actions, and then you have the signals descending in the brain to the brain stem, and from there into uh, the spinal cord, and from the spinal cord to the skeletal muscles. The motor neurons go from the spinal cord to the skeletal muscles and convey information. Now, of course, at the spinal cord, there is also the integration of the sensory inputs that are coming from the body and the motor inputs that are coming from the brain, and they are both combined together and used to control the skeletal muscles. Now, the spinal cord is quite complicated, as you would know, and you have sensory tracts which are ascending through the spinal cord to the brain, and you have motor tracts which are descending from the brain to the peripheral muscles, right? And the neurons that come out of the spinal cord form nerves, and these nerves include both sensory and motor neurons, and they go to the periphery of the body, right? So motor neurons end up in the skeletal muscle. The autonomic motor neurons end up in various smooth muscles in our body. These are muscles which are not under voluntary control. And then, of course, the sensory neurons end up in the various sensors distributed throughout the body. Now, if you look at the spinal cord, uh, the red parts in the spinal cord are the parts where you have the sensory neurons ascending into the brain, while these black portions, this portion, the corticospinal tract, lateral corticospinal tract, and the anterior corticospinal tracts are the tracts where you have the motor neurons the motor neurons descending from the brain down, right? So there is a clear division in spinal cord where you have sensory neurons and where you have motor neurons, right? Okay, so let's think about the peripheral nervous system then. So what are the elements of the peripheral nervous system? As we've already said, you have the sensory part and you have the motor part, right? And the motor part consists of these motor neurons, which end in the muscle. And the junction between the muscle and the nerve is called the neuromuscular junction. Of course, the motor neurons are myelinated, and because of the myelination, the conduction speed across the motor neuron is vastly increased. The sensory neurons are also myelinated, and the sensory nerve ends in a sensory receptor. Now, these receptors can be of various kinds. Let's not get into details there. And whenever the sensory receptors are stimulated, the nerve carries a signal to the brain. Now let's just think about the motor neurons in a little bit more detail. So here's a motor neuron, which is somewhere in the spinal cord. And from there, the axon of the motor neuron comes down and innervates the muscle. Now, when a motor neuron comes down, it does not just innervate one muscle, one muscle fiber. It's not as a one nerve fiber innervates one muscle fiber. Okay, a nerve fiber comes down and it innervates quite a lot of muscle fibers. So if you look at the cross section of the muscle here, you can see that a single muscle fiber is, a single motor neuron, alpha motor neuron, is innervating many fibers in this muscle. right? And therefore, when this motor neuron is going to have a signal in it, or let's say we stimulate it, or let's say the brain sends a signal and there's a action potential traveling through this neuron, many fibers in the muscle are going to be activated at the same time. So all these muscle fibers that are connected to a single neuron are together called a motor unit. Okay, and this will become important in neurological measurements, because sometimes what we want to do is we want to stimulate a motor fiber and look at motor unit action potentials, if we are able to do that. Okay, so those are motor units. Now the size of motor units can vary quite a bit. So you can have nerve fibers that are connected to many muscle fibers, and therefore you have a large motor unit, or you could have a very small motor unit, and it depends. It's not uniform. Okay. Now there are various kinds of motor units. Okay, so you have slow motor units. So slow motor units are motor units that do not get fatigued very easily. Okay, so they can go on for a very long time, but at the same time, the force that they can generate is very small. You have fast fatigue resistant, or let's go to the fast fatigable motor units. Now these are motor units which are large, which can produce a huge amount of force, but they fatigue or get tired very quickly. In between them are the fast fatigue resistant motor units, which can produce more force than slow motor units, but fatigue faster as well. Now, not only can they produce more force, so for example, the fast motor units not only can produce more force, they also switch on very quickly. Okay, and also notice here that these are getting fatigued very quickly, while the slow motor units can go on and on and on. Okay, and both are required, right? Because and you can see that because, well, let's say when you're standing, you can stand for a very long time because your slow motor units are on while the fast motor units are off. But you can exert much more, you can produce much more force than what is required for standing, right? Let's say when you're sprinting, you produce quite a lot of force, but you can't keep that for a very long time, because when you're sprinting, you're using your fast fatigable muscles and motor units, and once your motor units get fatigued, then you'll have to wait for them to recover before you can exert that amount of force again. So when you're generating force, what happens? If you are generating a very low amount of force, then you have these only the slow fibers getting recruited, right? Those motor units are firing. If you want a little bit more force, the fast fatigue resistant muscles come into play. And if you want a little bit more force, that's the time when the fast fatigable muscles also come into place. So as your force requirement goes up, more and more muscles are recruited. And that is one reason why when you're doing exercise, people would say you want to you want to do the exercise till the moment when you can't do any more, because at that point you have recruited all your muscles. Another way to think about it is when you're doing exercises, if you're doing a slow exercise, you can go for a very long time. Let's say a moderate exercise, you can go for a very long time, right? But if you are doing a bit of heavy exercise, you can't go for that long, because then what you're doing is you're trying to recruit these fast fatigable motor neurons. When you're doing exercise, many people would say that, let's say you're lifting weights, lift a heavy weight, and when you're lifting a heavy weight, what you're doing is you're employing the fast fatigable muscle fibers. When they are fatigued, then what you do, you can't lift that much weight. So what you can do is you can go to a lower weight and try to fatigue these muscles, the fast fatigue resistant muscles, right? Because they have not yet got tired yet. So you can lift a little bit lower force, and when these get tired, you can go to a still lower force and try to fatigue your slow muscles as well. And that's how you get all your muscles exercised. But anyway, I'll leave you to explore those ideas. Now, when motor units are being recruited, so for example, when I want to say I need to produce a certain amount of force, how does that work? So what happens is there are two ways in which you can increase the force that you're producing in your muscle. One is you can take a particular motor unit and increase the firing rate of the motor unit, right? So you can send more action potentials down the motor neuron so that the muscles contract more and more and more. Another way to do it would be to increase the number of motor units that are that we are using to increase the force. And both, so when you're trying to increase force, both play a role, right? So so if you want a little bit of force, probably one motor unit starts off, and then the firing rate goes up as you need more and more force. And as you need more and more force, more and more motor units are recruited, as well as the firing rate also keeps going up so that you can increase the force that you are using. Now, one of the things that you have to understand here is also the size principle. So when you are using the motor neurons, the biggest motor neurons are stimulated or are recruited or are used at the end because they are the most powerful. Unless you need that much amount of force, you don't want to use your biggest motor units. So when you're and that happens even when you're stimulating. So let's say you're stimulating a nerve, the first motor neurons that are going to be recruited are the very thin ones with small motor units, right, which have less force, which can be stimulated at a lower threshold. And then as you keep increasing the stimulation intensity, you get bigger and bigger motor neurons being recruited, and therefore bigger and bigger motor units being recruited, and more force being produced. So let's also talk about what is the kind of signals that you would record when you're recording from nerves or muscles. So if you have your active recording electrode here, and let's say there's an action potential that is traveling from from the left side to the right side, what kind of signal are you going to record? So as the signal travels towards the electrode, you have a positive swing. And then as this action potential comes directly under the electrode, you have a negative swing. And then as it moves away, again, you have a positive swing. And then so the basic shape of the signal is a triphasic shape, right? Unless your electrode is at a place where the signal generation starts. If it starts under the electrode, then you don't have that initial positive spike. Okay, you just have the negative and the positive spike. So those are the kinds of shapes that you would be recording from a muscle or from a nerve.